All righty, let us get started. So today is our last day of class. We will not be meeting on Wednesday for any reason. We'll do the final exam review today. First of all, the exam itself will be on Monday. Let's see, Monday, May 9th. So, of course, I think an email was sent. I'm not sure, but basically because of some percentage of the students seem to be coming down with COVID, the university is definitely allowing all final exams, if the faculty chooses to do so, to be done online. And so we will just continue, which is the plan anyway, but we will continue to have the exams online. So this exam will be just like the previous test, the mid-semester style test we've been having, where it's posted in the morning and you have till the evening to submit it. All calculation style questions, everything will be same format as the regular tests. The only difference, of course, being that this final exam is a cumulative exam. And so that means it's on all the topics we've covered over the semester. And so just as a quick summary of what I'll talk about today, best way to study for this test is to go back over the previous test. Look over the old tests. Those questions that were put on those tests were the questions I felt most important for the topics we discussed. And so likely for the final exam, I'll still find those topics to be the most important. That doesn't mean that you won't see a different question that wasn't on one of the previous tests on the final exam. But certainly the best, most efficient way to study if you have a limited amount of time is to first and foremost look back at the old test, try to rework them, have a blank sheet of paper, and just redo the test and see how you do. If you're working them all fine, you're getting all the questions right, then likely the final exam should be a piece of cake. Further from that, look at the homeworks that we had and the example problems we've been doing in class. Again, all these types of questions are questions that I make up. I don't look them up in a textbook or anything. So that's how my brain works. You see the style of question I think up. So likely test questions will look the same, very similar. And certainly, there won't be anything on this final exam that wasn't part of one of the topics we've already discussed. There's no new information, no new topics or anything. It's the same stuff we did. It's just a chance to say, okay, now that we're through everything, let's see what you remember. Let's see what you know from what we discussed this semester. That's basically what this final exam about. Things to note about it, about the formality before we get into the topics themselves. I am handling the test as if it were an in-class test, meaning it's going to be a 2-hour, normal final exam, 2-hour exam, which means it's about twice as many questions as a regular test was. So the regular tests were about 6 or 7 questions each. So the final exam, you can expect about 12 to 15 questions for the length of the test. Again, the format will be the same format as the regular test, all calculation style, show all your work, box your answers, things like this. You need, of course, your calculator, just like before, because you actually have to have real numbers. And that's the formality. The topics, basically there's 3 overarching topics, as there were 3 mid-semester exams. The first, if we think back to the beginning of the semester, the very beginning of the semester, when we did the math review stuff, there won't be anything on this test that's specifically just mathematical review. That math review was just to make sure that you're up to speed with the kind of math necessary for the course. But I won't have a question on the test that's something like, here's a vector and here's another vector, add these two vectors together. We won't have anything like that. Or here's a trigonometry problem. Rather, that was just stuff to review before you get into the physics. And so no math review specifically on this test, but obviously every single physics problem you do has some sort of mathematical basis in it anyway. So all the math stuff is tested in the regular questions. So where the actual material started was thermodynamics. Thermodynamics was our first topic, and that's what our first exam was for. And under this topic, we had a few different things. Firstly, we had calorimetry. And calorimetry dealt with the type of question that was, you have a hot cup of coffee, you put some ice in the coffee, you mix it around, and you want to know what will be the final temperature of the system. Or I want to bring down the temperature of the coffee to 80 degrees. How much cold milk should I add? Those types of questions. And so we had Q equals Cm delta T, which was the main calorimetry question or equation. This was the equation you use when the material is changing temperature, but not changing phase. Q equals M times L, that's the latent heat version. And this equation is used when, for instance, you have ice in your system and the ice is going to melt. Well, first you heat up the ice, that's Cm delta T, to get it to its melting point. But then when it melts, it's not changing temperature. So we need the second equation to tell us how much heat is used to melt that ice. And then once it's melted, you go back to Cm delta T to heat up that melted ice to its final temperature and so forth. And so the calorimetry stuff dealt with these two equations. You have a system, you put all these materials at different temperatures together, and they come to some equilibrium temperature, and you want to know something about it. What's the final temperature? How much material did you add? Things like that. Then from calorimetry, we went to heat conduction. Heat conduction was the kind of question where you have, let's say, a wall of a certain thickness, and it's made of a particular material, so you know the conductivity, K. And you're told the outside temperature is 100 degrees, the inside is at, I don't know, 50 degrees. And you want to know what is the heat transfer rate that flows through the wall by conduction. And so that equation was Q over T. That's the heat transfer rate, the amount of energy that passes per second, is K A delta T over L. K being the conductivity, that tells you about the material. A is how big is the material? What's the area of the wall or the window, whatever it is. Delta T, of course, is the difference in temperature between one side of the wall and the other. And then L was the thickness. How thick is your wall? And so you could figure out what's the heat transfer rate. And then you could also ask the question, how much energy will flow in one day? And in that case, you just move the little t to the other side and you say how many seconds are in a day, and you plug that in and multiply it out. And now instead of the heat transfer rate, Q over T, you're instead solving for the total heat that transferred. That's just Q. And then the secondary thing we had was, well, what if we have two materials that are touching each other? So a wall and some insulation. And you want to know the heat transfer rate through the system, the whole system, both materials. And we used the little fact that Q over T the heat transfer rate through the first material is the same as Q over T for the second material. So you'd set up a Q over T, this thing, for the first thing, equals that same thing for the second material. Now they're equal, and you can use it to solve, for instance, for the temperature in the middle and things like that. So those were the types of questions we saw with conduction. Finally, I believe the last topic was radiation. Heat transfer through radiation. And this is similar to conduction. Again, some amount of heat is being transferred. And so we want to know the heat transfer rate or the power radiated or things like that by something that's really hot. So you've all seen, you know, charcoal glows red, or a piece of metal, when you heat it up really hot, it starts to glow. That is energy, heat energy, radiating from the material because it's very hot. And so you may want to know how much heat is radiated per second because of its heat, and that, or because of its temperature, and that is sigma epsilon A T to the fourth. Here, sigma, remember that was called a Stefan Boltzmann's constant. It's just a number. Again, any constant like this, specific heat, latent heat, all those types of things will be on the test. You don't have to memorize them or anything. Epsilon, that tells you, that's the emissivity. That tells you how easily does our material radiate. Obviously, metal radiates very well. Wood does not radiate all that well. And so epsilon is some percentage. It radiates at 30%. So epsilon would be 0.3. Or it's a perfect radiator. Epsilon is 1 for 100%. A, that's the surface area. So basically, how big is the thing that's trying to radiate heat? The bigger the object, the more places that radiation can come from. And so more radiation will flow in a bigger object than a smaller object. And that's what A is. And then T, of course, is the temperature, T to the fourth. Here, the big thing that differs from the other equations we've been using is this is not delta T. This is temperature itself, the absolute temperature, which means this has to be in Kelvin. So you have to convert your temperature from Celsius to Kelvin for this one. You can convert the other ones too. In fact, that's actually the rule. You're supposed to always be in Kelvin. But we saw when we first went over this that there's a trick that anytime you have delta T, you could use Celsius instead of Kelvin if you want. Here with radiation, we don't have delta T, so you better convert to Kelvin first, and then you do the equation. And then we also saw if instead of just having the object radiate, we actually put the object in a background or in some other environment that's able to be at some other temperature, and it modifies the equation a little bit. It says sigma epsilon A, but now we have the temperature of the object to the fourth power minus the temperature of the environment to the fourth power. So this is used if I say something like you have a steel ball, which is at 500 degrees, and you place it inside of a refrigerator that's at 5 degrees. And I want to know how much heat would be radiated per second. Well, then I'd use the second one because the environment's at a different temperature than the object. And that's radiation. And so that is everything about thermodynamics. That was what we found out, or that's the kind of stuff we did for the first exam. The second exam, which means the second big topic we had, was about fluids. And so just like with thermodynamics, the topic of fluids has several subtopics associated with it. The first that we dealt with was Bernoulli. And with Bernoulli style questions, what we have is something like a pipe system with water flowing through the pipe or some other fluid, but usually we do it with water. And the pipe system can, change heights. It can go up to the second floor or down to the basement or all sorts of things. The pipe itself can change sizes, so it can expand or contract. And you want to know about the pressure in the pipe because of all these changes. And what we had is the Bernoulli equation, which says P1 plus 1/2 rho V1 squared plus rho GH1 is constant, which means if you look at all of this stuff at one point, that total number is the same as if you look at it at another point. So it's equal to P2 plus 1/2 rho V2 squared plus rho GH2. And so again, pipe system, the pipe contracts or expands. And the only other thing we need to know with this equation is if the pipe does change size, that affects the velocity of the fluid. And so if we have a change in the velocity of the fluid because we changed the pipe size, then we better know how the velocity changes. And that's through the use of the continuity equation. And it says A1 times V1, which is the cross-sectional area of the pipe times the velocity of the fluid in that part of the pipe must be equal to the area of a second part of the pipe times the velocity in that second part. Okay, so if you have a pipe and then you constrict the pipe, well, the velocity of the fluid must go up. The fluid speeds up such that the total volume of fluid that flows through that part of the pipe is constant. It doesn't change. If you constrict the pipe, there's less room, so the velocity has to go up to make sure you get the same amount of water through as in the big part of the pipe. And so with these two equations in combination with each other, you can solve those pipe system style of questions. Not all of the questions need you to use continuity equation. If you don't change the size of the pipe, the velocity doesn't change. If you don't change the height, then you don't need the terms with the h in it because they're the same. The height doesn't change. So make sure, as you saw in the test, that when you read the question, just because I happen to give you some information, that doesn't mean it's important. I know there was definitely a question on the test where I think I gave you the size of the pipe at the beginning, but then I don't tell you some new size of the pipe. I don't tell you the pipe changes. And of course, several people said, hey, look, you forgot to tell us the new size of the pipe, or some people used a different number to try to use as the new size of the pipe. But if the question doesn't say I constrict or I expand, then it doesn't. The pipe stays the same size. Now, if you want to be sure, definitely send me an email while you're taking the test and say, hey, look, I think this piece of information is missing, but I'm not sure. Can you let me know? Because of course I can make mistakes when I make these questions, definitely. But if you read the question and there's nothing in there about the pipe changing size, then just because I give you the size of the pipe doesn't mean it's necessary. It may just be superfluous information. You don't need it, which is good. So just be careful when you're working these questions that you know what's important and what's not. Well, from Bernoulli pipe system style questions, we also had the pressure depth relationship. And pressure depth relationship just means that when you're in a fluid, the further down you go in the fluid, the more pressure you're going to feel. So if you go into water and you're scuba diving and you dive deep, the pressure on you grows as you go deeper and deeper. And so we'd like an equation that tells us how big is the pressure if you're this far down underwater. And the equation is pretty easy. The pressure is equal to rho, the density of the fluid. So obviously, if you're in water, then there's going to be greater pressure than if you're in air, because the water is more dense, it's thicker and heavier, it pushes on you harder. Times G, 9.8, times H, which is the depth. How deep are you? So that's a pretty easy relationship. The only thing to go along with this is to note that there's two types of pressure you may be interested in. One is called the absolute pressure, and the other is called the gauge pressure. The absolute pressure is the total pressure felt by the object. And so that is whatever the atmospheric pressure is. So just the normal pressure you feel being here on Earth because the air is pushing on you. Plus the extra pressure because you're doing something, like you're diving deep in the water. There's going to be extra pressure applied to you that there wasn't before. And that's called the gauge pressure. Okay, so given a question like a diver dives down 20 meters under the surface of the ocean, what's the pressure felt by the diver? Well, that's asking me about the gauge pressure. However, if the question says what's the total pressure felt by the diver or the absolute pressure felt by the diver, now what I want is the actual total pressure, which is the gauge pressure, because you're this far under the water, plus the pressure you already felt before you even got in the water. So that's the whole gauge pressure versus absolute pressure thing. All right, then we had Archimedes. Archimedes' principle gave us several relationships. Okay, and these relationships had to do with things like buoyant force, why things float. How does placing an object in a tank of water make the water level rise? Things like this. And this is several different relationships, all that go together to help you do Archimedes' principle. And so the first one is that the volume of the water displaced, so you place an object in some water, the water level rises. That's called being displaced. You've moved it. So the volume displaced, how much water is moved, of course, is equal to the volume of the object that you put in there. You put a big object in, you move the water a lot. You put a little bitty object in, the water doesn't move that much. So the volume of the object placed in water tells you the volume of the water that was displaced because you put the object in there. Then the buoyant force, which is the thing that makes something float, the buoyant force is equal to the weight of the water displaced. So you put an object, let's say you have a cup of water and you put an ice cube in. Well, first, putting the ice in the water makes the water level rise by a certain amount. The amount is the volume of the ice cube tells you the volume of the water displaced. That's the first one. This one says, okay, the ice cube is floating. Well, the ice cube wants to fall by gravity, so there's another force pushing it up, making it float. That's called the buoyant force. How big is the buoyant force? Well, if you take the water that was displaced by the ice and then figure out how heavy that amount of water is, that's the same as the buoyant force felt by the ice. That's what this says. And so if we write it again using some other variables, buoyant force is the density of the fluid times G times the volume of the fluid. Okay, so the weight of the water is density times volume times G. It's the same thing. If you remember, density is M over V times volume. So M over V times V just gives you M. M times G is weight. So this relationship is just the second relationship where we look at what weight actually is as a calculation, and we write down the calculation. And then lastly, we write it down again, only now we use the top fact, the top relationship, and say the density of the fluid times G times the volume of the object instead of the volume of the fluid, because they're the same. The volume of the fluid is the same as the volume of the object. And so that's Archimedes. With this, you can have things like you place this object in this fluid. What's the buoyant force acting on the object? Or we can do what's called the apparent weight. Apparent weight goes with this. How heavy does something feel? Well, that's the apparent weight is the true weight, the actual weight of the object, mg, minus how much buoyant force is pushing on it. The more buoyant force, the lighter the object feels. So if you can calculate the buoyant force, which is what Archimedes lets you do, then you could say, okay, I'm a treasure hunter. I found this old Spanish galleon down under the water, and it's got a bunch of treasure chests. And I want to know how heavy the treasure chest is so I could design some equipment to pull it up. So how heavy will this treasure chest feel? Well, I know the actual weight of the treasure chest because of how big it is and how much gold is in it and blah, blah, blah. So all I have to do is figure out what would be the buoyant force on the treasure chest, which I can do from Archimedes. Subtract that away from the actual weight of the treasure chest. And now I know, okay, it'll feel lighter, and this is how light it'll feel. So apparent weight kind of goes with Archimedes a lot. The last thing with fluids was the whole percent submerged relationship. This little relationship is very, very nice because it helps you to solve very complicated sounding questions. For instance, here's a big old aircraft carrier. All these planes are on it, all these people, different rooms, different chairs, all sorts of stuff that composes the aircraft carrier. And you want to know what's the density of the aircraft carrier. Well, that's a very difficult and complex question because of all the different materials and all of that stuff you got to take into consideration. However, this says if you know how much of the aircraft carrier is submerged under the surface, the percent submerged, like 20% of the aircraft carrier is underwater, then it's very easy. Because what it says is the amount of the object submerged is the same as the ratio of the density of the object you're talking about divided by the density of the fluid that the object is in. So if I tell you the aircraft carrier is 20% submerged in some water, what's the density of the aircraft carrier? Well, it's just the density of the fluid, which is water, 1,000, times the percent submerged, which is 20%. So 0.2 times 1,000. So very, very nice relationship, makes a very complicated question easy to do. The key is, this is how much is submerged. You have to be careful when you're reading the question, especially if you're trying to rush through the test. It's easy to read the question that says, you know, 3/4 of the aircraft carrier is above the water. What's the density of the aircraft carrier? Well, in that case, 3/4, that's 75%, is above the water. But you want how much is below the water. That's what submerged means. So you don't use 3/4, you use 1/4. So you have to be careful when you read the question that you know the number that's given in the problem is the appropriate number to use. But other than that, it's a fairly straightforward thing. All right, the last big topic is what was on this last test, which is light and optics. So this you should be fairly comfortable with, since we just had a test on it this past week. But to go over the topics again, we first dealt with waves and the various characteristics of waves. We had things like the velocity of a wave is frequency times lambda. That's one big relationship we have to know. And of course, the velocity of light is called c, which is 3 times 10 to the 8th, a very famous number. But other waves have different velocities. Sound waves are 343 meters per second, for instance. In water waves, waves on a string, everything has different velocities. Light is a very special number. We also had things like the period. The period is 1 over the frequency. Okay, that's another relationship. We had things like angular frequency, omega, is 2 pi times f. If you know the linear frequency, f, then the angular frequency, you just multiply by 2 pi. Wave number, k, that's related to the wavelength, that's 2 pi over lambda. Now, these were important because we have the big equation, or the functional form of a wave is another way of saying it. And that is the height of a wave at a specific time and place is given by the maximum amplitude of the wave, A, times sine of kx minus omega t. And so that's why we need this omega and k, because if we don't have omega and k, if we write it as f's and lambdas, there's a bunch of 2 pi's everywhere, and it makes it look really messy. So we have the equation look nice, and thus we have to remember these other relationships about omega and k. But it's no big deal because they're pretty easy. And so that was the stuff about waves in general. Different characteristics. You have a wave traveling at 500 meters per second, has a frequency of 1,000 hertz. What is the period? And what's the wavelength of the wave? That's one thing. Or light has a wavelength of 50 nanometers. Write down the functional form of the wave. These are the types of questions where you use these relationships. Then the next subtopic we discussed was polarization. Polarization is a characteristic of light specifically. And if you remember, it basically defines the direction of the electric field. So the electric field will be oscillating in some direction. The polarization angle tells you what's the direction of the electric field. And the question is, if you have light that's polarized in some way and you send it through a filter, polarizing filter, how much light will make it through? This is where the law of Malus comes in, and it says the intensity of the light that makes it through is the initial intensity of the light before the filters times cosine squared of theta for each filter you have to go through. So if you have multiple filters, you have to multiply by multiple cosine squareds. And of course, remember theta Theta had to do with the difference between the angle of the light coming in and the filter it's trying to go through. And then also remember about unpolarized light says the first filter is 1/2. You don't need a cosine squared for the first filter if your light starts unpolarized. The first filter will give you 1/2, and then every filter after will have a cosine squared you have to do. Now, one thing I will note is I noticed when I was looking at some of the exam 3s for these polarization questions, a lot of people really tried to do things with the fractions. So, you know, cosine squared 30 degrees, for instance. Well, that's square root of 3/2 squared, which is 3/4. That's fine. But then when you start getting into things like cosine of 15, and you have things like square root of 3 plus 1/2, things get really messy, especially because you probably don't just have one filter, but you have multiple filters. And a lot of people obviously did a lot of work trying to multiply all of these fractions and stuff. That's fine. You can do it if that's what you wish. But my recommendation to you, because I've seen a lot of people make mistakes when they do it this way, is to just stick it in your calculator and get a decimal number. Some of the easy ones, if you want to do it by fractions, that's fine. But once you start getting radicals and square roots all over the place, it gets really messy, and it's really easy to make arithmetic mistakes with that kind of stuff. So I just recommend when you're doing the polarization stuff and you have your law of malice equation written out, don't be afraid to just use the calculator to get a decimal answer. That's perfectly fine. And it's a lot easier on your part. There's a lot less mathematics you have to go through to try to do it all by fractions and stuff. Lastly, last topic or subtopic is refraction. Refraction was the effect on light where light goes from one material to another, and so it path bends in some way. Light is incident on the surface of a pond at an angle of 30 degrees. What is the angle of refraction? This uses what's called Snell's law, and it says n1 sine theta 1 is n2 sine theta 2. And so n is called the index of refraction. That tells you what material are you in. If you're in air, n is 1. If you're in water, it's 1.33, and so forth. Theta, that's the angle that light makes with respect to the perpendicular line. So when light's coming in, hits the surface of the water at an angle of 30 degrees, that theta 1 is 30 degrees. Angle of refraction means once the light goes into the water, the second material, the light will bend, and so it refracts. The angle of refraction would be theta 2. What's the new angle that light makes because it's gone into the second material? The thing that goes with it is called the critical angle. And this is a form of refraction, but it's a special case where you're starting in the thicker material and you're going to the thinner one. And what happens is, for a certain angle called the critical angle, when the light hits the material and tries to go into the second one, it can't. Instead, it bends so much that it skims the surface. And so you just use Snell's law to calculate this. You'd say n1, oops, let me use blue again, n1 sine theta c, where that's the critical angle you're looking for, is n2 sine theta 2, but the critical angle is the special case where theta 2 is 90. So we happen to know this is 90 degrees. Okay, so it's just Snell's law. That's all it is. But you know, This is the critical angle. That means I'm looking for theta 1 instead of theta 2. What angle should I shine the light at such that theta 2 skims the surface? It's 90 degrees. Okay, so it's not two different equations. It's one equation, but you put the special case scenario in. And a special case means theta 2 is 90. What's theta 1, basically? And that's it. That's everything we've done this semester. So a whole bunch of topics: thermodynamics, fluids, and optics. 3 overarching topics. Let's just say, for the sake of making the numbers easy, there's about 15 questions. So think 5 questions per topic, something like that, at the most, probably less. I would imagine you're going to have a little bit of everything, probably at least one of each type. And then if there needs to be more, maybe 2 questions of refraction or 2 questions of the calorimetry or whatever. But certainly expect a question on each one of these subtopics just to be safe. But like I said, 12 to 15 questions is what you could expect. It's a 2-hour final exam. Even though it'll be held online, it'll still be the same length. I'm not making it longer. And you've already seen all of these topics on a previous test now, so you know what to expect. There's not going to be a drastic change in anything. If you could do the old test questions, the new final exam questions will be just about the same thing. So practice them, work them as much as you can to make sure you understand them, and then you'll be fine for the final. So, any questions for me about this final exam?
So you'll send it out like how you usually do the exams, and we got to 11:59 to complete it.
Yeah, exactly. I'll post it. So it's Monday, May 9th, this next Monday. I'll post it in the morning, just like usual. It's probably in the middle, early morning. It'll be posted. Download it, work it out on the test or on the separate sheets of paper, however you like, and then you submit it back, and the deadline will be midnight, 11:59 p.m. that night. Yeah, exactly the same as the old test. Any other questions about the formality or anything like that about this test? All right, well, I am still going through grading everything, making sure all the homeworks are graded. I know people are turning in their homeworks. In case you didn't know, I sent an email about it. I opened up all of the old homework assignments. So anybody that didn't turn in the homework when it was due, you have till I think this Sunday or final exam day, I forget when. It says on Canvas, but you have a few days to submit the homeworks if you didn't submit them before. So I'm still going through and grading that, and I'll have the exam 3 graded really soon as well. But as you're going through this week studying, if any questions pop up, anything you're curious about, feel free to email me. And if necessary, we could set up an appointment to do Zoom and to look at particular things. That's fine too. So don't be shy. If you need my help as you're studying, feel free to ask me questions. But basically, if you do the old tests and you look at the practice problems, there won't be anything on the final exam that you probably haven't seen before, other than the numbers being different. The style of the questions will be the same. So that's all I have. If you have no questions, you're free to go. And good luck on all your exams upcoming. I will see you on Monday.
Thank you. Have a nice day.
All right, you too. Thank you.